Okay. So, we have been doing calculations of magnetic field. Where we can use either the Biot-Savart formula or Ampere's law, which says that curl of B is equal to mu naught J r. This is in the differential form, and the integral form is that B dot d l is equal to mu naught times I enclosed. This is quite like what we were doing for electric field. However, if you recall, calculation of electric field was facilitated by the calculation of potential, because in the case of electric field, for electric fields, what we had was there was an electrostatic potential. Which was a scalar quantity. And therefore, if we calculated the electrostatic field, electrostatic potential, and then took the gradient of it, it gave me the electric field. The calculation of potential was much easier. So, the question that we are going to ask now is, can we define a potential for magnetic field also? And that is what we are going to discuss in this lecture. So, our topic in this lecture is going to be potential for magnetic fields. And you will see that the potential is not quite like the electrostatic potential. So, so life does not become that much easier as in the case of electrostatic fields. Here the potential is a vector potential. We will still leave the question is scalar potential possible for magnetic fields also. I am leaving this question open right now, but vector potential we can certainly work with, and for this I am going to make use of Helmholtz's theorem. Recall what it said. It said that if a vector field is there, let us call it B right here, it is well known if its gradient and curl is known. So, its divergence, for a magnetic field, for a vector field, there is a divergence. So, Helmholtz's theorem says that the field can be determined completely if its divergence and curl are known, and the way it is given is minus 1 over 4 pi grad of integral divergence of B at r prime over r minus r prime dV prime plus, and let me write this term here, 1 over 4 pi curl of B r prime over r minus r prime d v prime. Recall that for electric field, and I will emphasize it was electrostatic field, curl of E is 0 and divergence of E by Gauss's law is rho over epsilon 0, and therefore, we could write a electrostatic potential as integration 1 over 4 pi epsilon 0 rho r prime over r minus r prime d v prime. This is what we did for the electric field. Let us come to the magnetic field. And for magnetic field, what we have learned is that divergence of magnetic field is 0 and curl of magnetic field is mu naught J. So, let us go to the Helmholtz's theorem and substitute. Again, let me write what the theorem says. It says that I can write this field B r as minus 1 over 4 pi grad of divergence of B, this is at r prime, so I will put a prime in the divergence also, over r minus r prime d v prime plus 1 over 4 pi curl of B r prime over r minus r prime d v prime. Now, for magnetic field, we have divergence of B is equal to 0 and curl of B is equal to mu naught J r z r. For r prime, it will be curl of B of r prime is equal to mu naught J of r prime, and therefore, I have the magnetic field B at r is equal to curl of mu naught over 4 pi integration J r prime over r minus r prime d v prime. I am going to call this quantity A. So, I have B at r is equal to curl of A of r, where A of r is equal to mu naught over 4 pi integration J r prime over r minus r prime d v prime. This is known as the vector potential for magnetic field. Now, recall that for electrostatic field, I could add to the potential any constant, and the potential still gave me the same electric field. So, the electrostatic potential was defined up to a constant, In exactly the same manner, I can now add anything, the gradient of anything to this vector field or vector potential, and this will still give me the same magnetic field. Let us see how. So, I wrote A of r is equal to mu naught over 4 pi integration j r prime over r minus r prime dv prime if we add to this a gradient of some function f r to a above, curl of a is still b, because curl of gradient of a function is always 0. This is a mathematical identity. So, we can say that vector potential is defined up to gradient of a function. That means, I can add gradient of any function to this potential, and I still get the same field. This implies that A r is not unique. For this particular definition that I gave you, where I have given this expression A r is equal to mu naught over 4 pi integration j r prime over r minus r prime dv prime, I like you to show that divergence of A given by this expression is 0. To show this in your proof, you will make use of gradient of 1 over r minus r prime is equal to negative of gradient with respect to primed variable 1 over r minus r prime. So, I am leaving this as an exercise for you. What it also means that if you calculate A by some other means, which I will show in a minute, I can always add some gradient to it, so that its divergence can be made 0. What it means is, this implies that if divergence of some A that you have calculated is not equal to 0, you can make it 0 by adding grad f to it. How so? Let us check that. So, suppose I have some A 0, so that divergence of A 0 is not equal to 0. I can define another A, which is A 0 plus grad of some function. Then I can write divergence of A is equal to divergence of A 0 plus grad square f. So, Laplacian of f would be equal to minus grad of A 0. This is like the Poisson's equation for f. So, we can always find an f. And f to add grad f to A naught, so that grad of A is equal to 0. So, we can always make grad of A equal to 0. So, on this topic of vector potential, what we have is A r is equal to mu naught over 4 pi integration j r prime over r minus r prime d v prime. Component of A, let us say A I, is going to be equal to mu naught over 4 pi integration j ith component r prime over r minus r prime d v prime. Then you can see that del square A I will be equal to minus mu naught j I r prime. You can see that easily by comparing with the Poisson's equation for electrostatic potential and its solution in free space. This time I am going the other way. I have the solution, and from there I am getting the Poisson's equation. So, if I solve this equation and still find that after I have solved it that divergence of A is not 0, I can make it divergence less by adding some quantity to it. So, we found the equation also. So, in general I will write for all three components that del square A is equal to minus mu naught j vector r. This is the differential equation for j of r, A of r. So, I can solve this by some other means also. Let me now spend some time on physical interpretation of A r. Does it have any physical interpretation? Recall again that electrostatic potential is the work done in moving a charge through an electric field. There is no such interpretation for vector potential. However, you can get some idea about what it could be related to. So, what could A be related to? I am asking this question, and for this I will do dimensional analysis. So, recall that B is equal to curl of A. So, as far as dimensions of A are concerned, they are going to be the magnetic field times the length. I can write this as V B q divided by q v times L. I am doing this because q v b is force. So, I can write this as m L T inverse L divided by q L T inverse. Made a mistake? This will be T minus 2, because that is the force. So, this comes out to be m L T minus 1 over q, implies q times A has dimensions of linear momentum. So, we will see in some other courses, or you may have seen it in your classical mechanics, that q times A is added or subtracted from linear momentum of a particle to define canonical momentum. So, this is somehow related to the momentum of a particle. Beyond that, we will not go right now. So, what I will do now is solve one example of calculation of A. A sheet of charge of let us say not charge, a planar sheet in the xy plane and let this sheet is of infinite extent, carries a surface current density k equals k in the x direction. Find the corresponding vector potential. So, what you have been given is that here is the sheet in the xy plane, it carries a current, surface current k equals kx unit vector in the x direction. We want to find the vector potential. If I found the magnetic field and then calculated the vector potential, that is actually counterproductive, because I really want to calculate magnetic field through the vector potential. But just to give you a feel, I will first do a calculation through the magnetic field, and then we will do it directly by integration. So, B, if you recall the problem that we solved for exactly the same current configuration earlier, is given as mu naught k by 2 with a minus sign y for z greater than 0, and this is given as mu naught k over 2 y for z less than 0. So, B has only y component. And B, which is curl of A, is therefore going to be equal to the y component. So, partial A x over partial z minus partial A z over partial x. Now, I have freedom in choosing A x and A z. Let me make one particular choice. I will take A z to be 0, and therefore, A x will come out to be, just by inspection, A x will come out to be mu naught k over 2 z with a minus sign. So, A I can write as minus mu naught k over 2 z in the x direction, that is it. The other possibility is that I will take A x to be 0, and therefore, just by inspection I will take A z to be equal to mu naught k x by 2. So, that A will be given by mu naught k x by 2, and this is a z component. So, in the z direction, you can easily check that the two A's differ by gradient of a function. So, I just to give you a feel for A and to show you that they can differ, there can be many different A's that give you the same B, I just calculated this using the B field. Let us do a direct integration calculation also. Direct calculation of A. Recall the formula that I wrote. A at r is given as mu naught over 4 pi integration j r prime over r minus r prime dv prime. Now, in this case it happens to be a surface current. So, I can write this as mu naught over 4 pi integration k in that plane over r minus r prime ds prime, where ds is the area element in the x y plane at x prime y prime. If you want to see this transition from the first formula to the second, I can write for this planar sheet, which is in the z equals, let us say, 0 plane. I can write j r prime as equal to k in this plane. So, let me write this as in the x y plane times delta z, d v being ds prime d z prime. You can see immediately how you go from one formula to the other. In the present case, therefore, I have A r is equal to mu naught over 4 pi, k comes out, integration ds prime over r minus r prime, and this is over the x y plane. This is a very easy integral to do, and I will tell you that trick, and let me write this first. You will find that many integrals in magnetic field, comma, vector potential have a counterpart in electrostatics and are therefore well known. So, you do not really have to calculate them, use that in your calculations. So, to come back to our calculation, what we are calculating is this A vector which is mu naught over 4 pi k integral d s prime over r minus r prime over the x y plane. So, if you look at this integral is related to the electrostatic potential of a uniformly charged sheet in the x y plane. So, if I take the sheet z equals 0, it carries a uniform charge sigma. I know that the field is sigma over 2 epsilon 0 in the positive z direction above the sheet and sigma over 2 epsilon 0 in the negative z direction below the sheet, and therefore, V z, which is 1 over 4 pi epsilon 0 integral sigma d s prime over r minus r prime, is nothing but sigma over 2 epsilon 0 with a minus sign z. So, as z increases, take the sheet, V z decreases, becomes more and more negative. Similarly, on the other side, it should decrease because the field is the other way. So, I should put a mod here. Therefore, this immediately tells you that integral d s prime over r minus r prime is equal to, or let us put 1 over 4 pi also, epsilon 0 cancels, minus mod z over 2. And therefore, a r is going to be equal to mu naught k over 2 mod z. That is the answer. And it is in the x direction, the current is in the x direction. I had not put it here, so I should put it here. Let me see in the previous page. I had not put it there also, but I correct myself. So, this is the answer. Which is equal to whatever that plus sign minus sign, mu naught k over 2 minus z for z greater than 0 and plus mu naught k over 2, there is a minus sign in front, z for z less than 0. So, you solve the problem. You will see for other problems also, as I have written in the previous slide, that you can always find an integral corresponding to the electrostatics, and then just use that rather than doing the integration all over again. So, I will now summarize this lecture. So, what we did is we defined the vector potential for magnetic field B. Try to understand what this potential may mean physically, and finally did example for calculation of vector potential. Thank you.